Hi, everybody. So today I want to give lecture 2 for the category series crash course, lecture series for quantum formalism. So you'll remember last week we talked about like what is a category. We talked about, bring it up here, what is a functor, and we gave many examples. And you'll see we have a bunch of things in red here. These are all things that were part of the exercises for last week. And yesterday we gave the first problem session where we kind of go over all these exercises and go over little other examples related to those exercises, fill in some details from the actual lecture itself. So one of the last things we did in lecture 1 was talk about functors and natural transformations. So I'm going to quickly recall what those are. So given a category, or given two categories rather, categories say C and D. Oh, it's supposed to be a script D. It's really terrible. A functor, say F, big F, from C to D. It's a way of associating objects in one category C in another category D. So it's sort of like a function between categories is the way you should think about these. Or maybe a structure-preserving morphism. I think that's how you spell preserving. Something about lecturing where it makes your entire brain just kind of leak out your ears as you're speaking. Structure-preserving morphism between categories. So we saw that a functor is a way of associating you get a function on objects. So from the set of objects of C to the collection of objects of D, right, so you said X, say, goes to some object f of X. And you can also define for any two objects, X and Y, you define a set function. To the set of morphisms from f of X to f of Y. You send a function f, little f, to, say, big F of F. Here's something I didn't mention last time. A little note that we'll use later on in this section. Sorry, I'm trying to make sure my stuff doesn't fall off the desk. So some extra things here. We talked, when you learn about sets and functions, you learn about stuff like an injection or surjection. For categories and functors, you have a similar concept. So a functor from, say, C to D is full if the following happens. So for any two objects in C, the set function from the set of morphisms from X to Y into D, is surjective. Is surjective. Likewise, let's say the functor from C to D is faithful if the same function from x, set morphism from x to y into set morphisms from f of x to f of y is injective. So again, this is for any choice of elements or objects x and y. So it's faithful. The names are kind of dumb, but here. So the last thing is, so like we have injective, surjective, bijective for sets. We have full, faithful, and fully faithful. There's no new word here. So F is fully faithful. If the same map is a bijection. If, so, dot, dot, is a bijection. So in this case, if you have a fully faithful map, so just take this thing again, so I don't have to rewrite it. Copy. So in this case, I guess I have to write it again. If I have a bijection of sets. So every morphism from x to y is, in bijection with some morphism from f of x to f of y. Just because, this is the idea is that, if you're associating some function over here, it's just sent to some function over here. It doesn't necessarily mean, there's a unique way of representing these things. So this comes up a lot frequently in the concept of subcategories and full subcategories. So, subcategories. So, for example, if I have the category of finite sets, maybe I'll write like a fin set. This is a subcategory of the category of sets, right? And this just means, the category of finite sets is its own category. So any finite set is itself a set. So I'm just sending it to, so I have kind of an inclusion functor. Inclusion functor. It's just sent to itself. And any function between finite sets, there's no extra kind of information we're losing. So this is, if x and y are both finite sets, then this morphism f just goes to itself. So we'd say in this case, fin sets. So if I have not here, x and y, it's the same thing as a set of morphisms from x to y. Just consider them as sets and not finite sets. Oops, I'm stuck on that here. Likewise, this is in a case a full subcategory. You also have the category of finite dimensional vector spaces. So this is category of finite dimensional vector spaces over a given field. Over a field K. This is a subcategory or a full subcategory of the category of vector spaces. Again, you kind of have an inclusion functor. It's usually right as I or iota. And this is a full subcategory because, so I didn't really define what that means, but in general, for a subcategory, you can have that this is just a injective function. Like maybe, if I have, I'll come up with an example. We'll do that for the problem section for this week. We'll talk about that one on Sunday. Two vector spaces V and W. It's the same here. I don't lose any more data by only considering them as finite dimensional vector spaces. So we're going to see a really important morphism here. Construction here for something called the Yoneda lemma coming up, where you care about a certain full subcategory of a really big category. So let's talk about that right now. So first, what I want to do is kind of come back to the problem we had last time. So the final problem in the exercises from last time was about a transformation between two functors. So this kind of brings us into our whole natural transformations thing. Natural transformation. So this is just a fancy word for talking about morphisms between functors. So if I have two categories, C and D, and I have two functors between them, let's say G and F, well, just like we had for this central question for central motivating thing for category theory, was given any kind of structure, I want to look at the collection of all structures of that form. We're kind of pulling this again in a little bit of a meta sense to look at morphisms between functors. Where were we? All the way down here. So given this, what is a morphism between F and G? Oops. I'll call that eta. I can look at now sort of like a category of all functors from C to D. So what it should do is associate, for any object X in C, a morphism between f of x and g of x in D. Oops. Bring that up here. This is sometimes called the component of eta over x. And for any morphism, let's say little f from x to y, we have a commutative diagram. Oops, jeez. This pen tip is a little loose. Commutative diagram. Okay, so what do we have to keep track of here? So we have a morphism between f and g applied to x, to the component of eta over x. I have a morphism between f of y and g of y, which is the component of eta over y. And each one of these functors, f and g, defines a function. F applied to little f and g applied to little f. So what I require for a morphism between functors is that this diagram always commutes. So you can either, you could start over here and then apply big F of f and then apply eta sub y, or you could go from f of x to g of x and then g of y, or g of x to g of y. So what we're saying is, when I say this thing commutes, I mentioned this a few times last week, is that g of f of eta sub x is equal to eta sub y of big F of f as functions or objects in the category D. Okay. So this is such a morphism between functors is called a natural transformation. What we discovered last week is that, and in the problem session, is that if I have the identity functor on the category of vector spaces, I'm going to call this thing, just to make it a little brief, like bold 1 sub k. So this is the functor on the category of vector spaces that just sends everything to itself. It sort of does nothing. So this is the identity functor. And then I had a sort of dual vector space functor, D, which goes from the category of vector spaces, opposite into the category of vector spaces. Right, sends V, a vector space, to the set of linear functionals on V. The set of k-valued functions on V. Call that D of V. And so we see right now that I sort of don't have any functions between these two, or any natural transformations between these two functors, because they're sort of defined on different categories. So there does not exist a natural transformation from the identity on K to the duality functor, because they're defined on different categories. The commutative diagram we'd want to draw right here wouldn't work out because the direction of the morphisms would go the wrong way. But there is one. This does work for the functor d squared, the double dual. In fact, we saw that there is a functor from the identity into the double dual functor. It's just a natural transformation from this functor to that functor. And if you restrict the subcategory of finite dimensional vector spaces, so if this is the identity on the category of finite dimensional vector spaces, and I have the functor d squared, or double dual, restricted to the category of finite vector spaces. Finite vector spaces. This is actually an isomorphism. This is something I asked you guys to find last time. This is actually an isomorphism. And the way you say that, or the way you phrase that, is that a finite dimensional vector space is naturally isomorphic to its double dual. This natural thing is sort of like that there's like a God-given isomorphism here. You don't have to, define it. We'll go into that a little bit more later on. Not this class, but next time. Okay. So that was a little example for natural transformations, functors, and all this other stuff. So the main subject for this lecture is the following. This is something called the Yoneda lemma. So we talked a lot about these abstract functors, all these kind of abstract nonsense so far. Let's talk about a really concrete thing. So for any object X in some category C, we can define some kind of easy functors. We know that, and let's say, and any Y in C, the collection of morphisms from X to Y is a set. It's an objective set. And so what I can do is, maybe I just forgot that Y was ever there. And I want to say, well, let's say I look at this. I kind of don't define Y, or don't specify what Y is. This actually defines a functor from the category of sets, the category C to the category of sets, where it sends an object Y to the set of morphisms from X to Y. Sometimes we'll call this functor H sub X. So I define it on objects. We have to see what it does on functions. So if I have any function, let's say G goes from Y to Z, what happens? What is this functor applied to G? This sends a morphism from X to Y to a morphism from X to Z. Okay, let's bring this guy over here, down here. So if I've got some morphism, little f, from X to Y, and I want to produce a morphism from X to Z, all I have to do is compose the two. So if I do F first, then apply G, I get a morphism from X to Z. Which is G of F. You can think about it like this. Cool. Sometimes we'll write, that this morphism, so this is sometimes written as G lower star, which is the push forward along G. Because you have a morphism from X to Y, you sort of push it forward along G, is the idea, to produce a morphism from X to Z. Okay, this is a nice little functor here. And likewise, I could do, I say, for any object x, I could do the morphism from this way. I could, think about x as being in the second component. So we see, instead of plugging in x here and not fixing y, I want to put x in the second argument and then not fixing the domain of this. So it sends any object y to morphisms from y to x. What does this do on functions? Well, let's see. So if I've got a function from y to z, and I want a function between these two things, how do I produce one? I can't really do the same thing I wanted to do before. So if I had, this morphism from y to x, it does not produce in like a natural way a morphism, come on now, from z to x. You can't really compose anything here. But if I started with the morphism from z to x, I can compose, right? I could send g to f of g. And so in fact, given a morphism from y to z, you get a morphism going in the opposite direction. So this thing I'm going to call h sup x. This is h sup x of y. So I take a morphism from z to x, and I send it to a morphism from y to x by composition. So oops. Via first sending it along g. Wow, come on now. Other way around, I think. Whoa, come on now. Sorry, I'm getting a little frazzled because my little pen is being crazy. So we pre-compose with f here. So if I send, in this case, I call this the pullback along G. So it sends the following. So here. And since I reverse the order of my morphisms, this is actually a functor that goes from the opposite category. This is a contravariant functor. It reverses the order of my morphisms. So if I have a map from y to z, I get a map from h of z to h of y. Here. Okay. So let's look at the following now. I'm going to look at the set of natural transformations between something of the form h of x. What does maybe natural transformation from h of something of the form h to the x from some other functor g look like? Some other functor g from the opposite category of C into sets. I'll call that eta. So this is sort of the central question that the Yoneda lemma answers. This is the context of the Yoneda lemma. Okay. So let's answer it. First, I'm going to say that we'll denote by C op set as the category of contravariant functors from C to set. So we talked about, functors and the morphisms between functors. So this is a well-defined category. So the question is, what is this set? So the Yoneda lemma, is that this thing is isomorphic, or in bijection with, as sets g of x. So every natural transformation, let's say eta from h to the x, or I'll write it as this, every one of these things corresponds uniquely to some element in the set g applied to x, whatever the functor g is. This is a bijection. So we're going to prove this. So in particular, the following happens. In particular, if g is another functor of this form, h to the y, the set of natural transformations from h to the x to h to the y is in bijection with this set, right? So this says it's h of y applied to x, but this is exactly, by definition, the set of functions from x to y. There is a bijection. So we'll go through and prove this. We'll see why it's useful and why this ends up being sort of one of the core, most important lemmas in all of category theory. When I first learned this class, I learned this subject, we were just kind of told, oh, everyone should prove this on their own once. Everyone should go through and just prove this. So they cheekily just said, left as an exercise. And in a sense, the proof is really easy, despite its fundamental importance in the subject. So if you really want to challenge yourself, stop the video now. Just go ahead and prove this. All I'm doing at the end for the rest of this video is proving this and maybe going over a few examples. But those examples we'll also talk about again in the problem session. So if you really want to challenge yourself, stop now and prove this yourself. And even if you're planning on watching the rest, I would stop for 5 minutes and just think about how do you prove this given the stuff we already know. We're not using any new techniques. We're going to use what we already have and be kind of clever. So we want a way to associate any natural transformation eta from h to the x to g to some element, say psi, in g of x. Or vice versa, any element of the set g of x uniquely determines some natural transformation. Let's get a bijection here. So what are we going to do? What I'm going to say is, well, let's apply these things. So what do I know about my axioms of a category? I know that for any category or any object x, there's always some identity morphism here, right? Identity from x to itself. That always exists. The generality of this statement, holds for any category C and any functor G. So we have to go to our bare bones assumptions. I know that identity always exists. And so if I have this natural transformation eta, I have a function. The component over x sends something into g of x. So why don't I just say the identity in here? Why don't we define this thing to be eta? In here. Okay. So I've now constructed some set here, or some element of the set g of x. The question is the hard part, which now, I've kind of given you guys a little bit of a mercy. Instead of making you prove the whole thing and identify how to make this association, I'm just going to make you do the rest from here. Show that eta, which what we defined was, wow. I'm kind of being an idiot. This is an eta, and this is a psi. Sorry about that. I have lost my mind. G of x determines, so this is maybe exercise 1, determines the component eta over y for any other element y. So I'll say it uniquely. So in a sense, if you understand what happens to the identity on x, you understand what happens to every other morphism from y to x. Okay. So what this is just defined, we have some natural transformation. We know h of x goes to g, eta, oops. Gets sent to this element. Okay. So that's the hard part. Now, exercise 2. Wow, my pen is really bugging out. Show this as a bijection. Okay. Now I'm going to go back into this context, this sort of isomorphism right here. So if we assume we already know Yoneda, then what this says is that the set of natural transformations set between h to the x and h to the y is just the set of morphisms from x to y. So what does this tell me, actually? Well, I can define a functor. Let's say from the category, I'm going to write it like this. From the category C into the category of functors, contravariant functors on C. So this sends any object x to the functor h to the x, which we saw was blank into x. So if I define this functor h hat, what the Yoneda lemma says is that by Yoneda, h hat is fully faithful. Ooh. You hear little people downstairs, sorry. And sometimes we call this a fully faithful embedding. It sort of embeds C in this larger category of functors on C. Embeds C as a full subcategory of the category functors on C. Why do we care about this? Well, we'll see next class. So next class, we'll see that this category of functors is sometimes called pre-sheaves. It's sort of just a nice kind of enlarging of C. It's much nicer. Than C itself. Like certain properties that might hold in C, might not hold in C, will hold in this larger category. There's a really nice analogy here with analysis. So in analogy with analysis, once we go through, single variable calculus, single variable analysis of real variable and everything, we start learning about distributions. You can embed smooth functions. Distributions. you send some smooth function to, yeah, I'm playing hard and fast with the rules here, to the distribution here. You sort of enlarge in the category of smooth functions to a bigger category where more properties hold. You should really think about this thing as the sort of analogy with C kind of embedding into the category of functors on C. You know, you want to sometimes restrict to certain categories. Like in this case, maybe you want G to be with compact support. Or maybe you want it to be like rapidly decaying at infinity or something like this. But you can actually make this precise without this category as well. It ends up being really nice. You can likewise define a sort of topology on this guy. On this category. You know, where you give, instead of distributions, some sort of weak topology given by sequences and convergence of those. You can also do a similar thing with this functor category. So what this Yoneda embedding does is identify a full subcategory. Yoneda gives a full subcategory of functors isomorphic to h to the x for some x. In general, if you have some functor, so if I have G is isomorphic to h of x for some x, I call the functor G a representable functor. These will be sort of a fundamental importance in category theory. I actually saved a little picture. Oops. Image. Don't worry about the pictures of my girlfriend and her cat. Oh, geez. So, if you can see this now, this is from a beautiful website called NLab. So representable functors are ubiquitous. And I really enjoy the following statement here. Category theory is all about representable functors and other universal constructions. They're sort of some of our biggest, most important objects we'll see in category theory. And I like this, also another analogy here. Listing examples of representable functors in category theory is like listing examples of integrals in analysis. You can always do so. You can always find more and more to list. And any list you find is always going to be incomplete. There's always something else you missed. So I'm going to shrink this. Here, put this over here. So I'm going to do a few brief examples of, I'll do one example right now of a representable functor we've already seen. So last time I mentioned in the problem session 1, we saw the following functor. So for any set X, I wrote script P of X for the power set of X. So this is the set of subsets of X. So what I saw in the problem session was the following. So previous, the power set of X was isomorphic to the set of functions from X into the two-element set. Oops. So you send a subset of X here into the characteristic function of that subset. So this is the function psi sub A, which says, for any given element little x, it's either equal to 1 if little x is indeed an element of A, and 0 otherwise. But in fact, I was being very sneaky, because you can also represent the power set as a functor from the category of sets to the category of sets. In fact, it's contravariant. Right? If I have a function, let's say from x to y, you get a function between p of y and p of x. Determines because you send a subset and say B here to the preimage of B, which is in here. So it's indeed a contravariant functor, but what we showed is actually the power set functor is a representable functor. In fact, it's naturally isomorphic to the set of morphisms into 0 to 1. This ends up being a super important thing, and this is because in the category of sets, in set, this thing here is something called a subobject classifier. In fact, the following statement is pretty cool. So you can say for any category C, in fact, you want something called like a small category, but that's not really that important right now. You can look at the functor, so, and let's say object X in C. You can say, well, what are the subobjects of X? This is a set. You can define this thing as a functor, if you're careful, from C op into set. And whether or not this thing is representable is whether or not the category itself, C, has something called a subobject classifier. So I'll go into that maybe in a class or two. Whether or not sub c as a functor. Wow, come on now. Is equivalent to C having something called a subobject classifier. So I might talk about this in a class or two. I'll call this some element omega in C. These are really important in logic, in categorical logic. In categorical logic. Topos theory, which I mentioned in the problem set session, and a lot of other things, and like fuzzy logics and other things like this. Okay, so I'll leave you guys with one more exercise, and then we'll be done. So exercise 3, I guess. So I initially did the Yoneda lemma over here for contravariant functors, right? But I could have easily done the following. I could have instead asked for covariant version. So define and prove a covariant version of the Yoneda lemma. So this is for functors of the form h sub x, which was from x into blank to objects, or to functors g, or maybe f, we'll say. In the category of functors from C into set. So instead of C op, we're doing C. So this is the covariant category, covariant functors. Oops, come on. So show, in this case, C to set from h sub x to f is the same thing as f of x. And I want you to understand, or to prove the equivalent thing for the Yoneda embedding in this case. So you have a functor here from C op into C set. And analog of Yoneda embedding for covariant functors. Okay, so there's 3 exercises. Oops. There's fewer than last time, but they're all kind of a little bit harder. All right, that's all for this week. I'll see you guys again next Sunday for problem session number 2. All right, bye.